Hey guys, today we're going to talk about exothermic and endothermic reactions and or what we call enthalpy changes for a given chemical reaction. So enthalpy. And if we look at enthalpy change for a chemical reaction, that enthalpy change, so it's going to be a change, right? So enthalpy is a fancy word for heat energy. And what we'll be looking at is basically delta H, right? So if we say if a reaction's endothermic or exothermic, what we're actually looking at is an enthalpy change. And the symbol for that is delta H. H for, if you want to, for heat energy. All right. And so what we see here are two different energy profiles for either an endothermic or an exothermic reaction. Remember, one of the signs for a that we could use to see if a chemical reaction actually took place would be a temperature change, right? We said that the temperature could either go up or go down. And so if the temperature goes down, what that means is that the reaction is absorbing energy. Oops. So temp goes down, right? This tells me that the reaction is absorbing energy. And so that reaction has to absorb energy in order to work. And when it does that, what we say is that that reaction is then endothermic. And when a reaction is endothermic, we say that delta H for that process will be positive because energy had to be absorbed when we are looking at it. Now, if we're talking about an exothermic reaction, for that particular reaction, we're going to see the temp around it goes up. Think about fire, right? So fire is hot. Temp goes up, right? It would be an exothermic reaction, and delta H for that process is going to be negative, right? And negative meaning that that energy is given off. So gives off energy. Whereas an endothermic, we absorb energy or take in energy. Okay, now, why does this happen? Why does a chemical reaction either take in energy or give off energy? Well, let's take a look at the reaction profile and kind of see what it's all about. Okay, so here you can see where we have our reactants right here. So our reactants always have a certain amount of energy, and the reason why they have a certain amount of energy is because they have some bonds that kind of have some energy kind of quote unquote stored in them. And then what we do in order to get any chemical reaction to work, we have to put in energy, right? And so activation energy is what we see here is the energy that you have to put in order to get a reaction to start. So that activation energy. So activation energy, we're going to put in energy put in. And this goes for any chemical reaction. It doesn't matter if that chemical reaction is endothermic or exothermic, we're always going to put in energy. And you may ask, well, why is that? Why do we have to put in energy if the reaction is exothermic? Well, in order for that reaction to go, if we kind of look at the combustion of methane here, CH4, right? We see at some point in time, in order for this to go to our products, right? In order for us to get over here, something had to happen. Something had to happen with the methane and the oxygen in order for them to get rearranged to give us CO2 and H2O. Okay, and so what's going on is if we draw the Lewis dot structure for methane, we see that methane would have 4 single bonds with hydrogen, and oxygen is actually going to have some double bonds, right? Now, we see this, and this is what they are, but we don't want to get those. We need to get them over here to be CO2, right? Or H2O. So if we look at the H2O, well, we only have one CO. Sorry. only have one of those. So if we look at the H2O, it's like this, right? And there's some lone pairs there. Okay, and so, well, how does that happen? Well, the activation energy is basically what happens. So first off, what we have to do, the reason why we have activation energy is that we have to put in some energy to break the bonds between the reactant particles. And that's what activation energy is. We're putting in energy, but we're putting that energy in to break bonds. All right, so that should make sense, right? To break something, you have to put some energy in. Now, you can see that both sides also have a downward kind of arrow, right? So sometimes they're longer, other times they're not, right? But that kind of hump comes back down. And why is that? Well, the reason why that is because these bonds over here actually have to form, okay? And so anytime that bonds are formed, energy is released, right? So here, this is energy released as bonds are formed. Okay, so we have to put in energy to break the bonds. We call that energy activation energy, and then we get energy that's released as bonds are formed. The more stable the bonds, the more energy that gets released. So in this case here, right, if we're looking at an endothermic process, the reason why is, well, why is it endothermic? Well, we had to put in more energy to break the bonds than were given off when these bonds were formed, right? So these bonds here, right? And basically what that means is that the bonds of the reactants were more stable than the bonds of the products. And so we had to put more energy in to break them. Over here for the exothermic, the bonds of our reactants weren't quite as stable as our bonds of our products, and we were able to release more energy. And so in each time right here, if we put in more energy than we get out, it should make sense that energy is taken in. So delta H of this process would be positive. Here, we're getting out more energy than we put in because these bonds are more stable. And so delta H over here is negative. Okay, and so tomorrow in a lesson, we're going to learn how to kind of calculate this during an experiment. But what we'll see and what we know is that for most chemical reactions, lo and behold, delta H is already known for that particular chemical reaction. So if we have the combustion of methane, and we see that that reaction is exothermic, and we know it's exothermic because that negative sign right there, and that negative sign is just a direction. It's telling me that it's releasing energy, and then we can see the magnitude of the energy. We're getting 802 kilojoules of energy out of that particular chemical reaction. So it's a pretty exothermic reaction. Now, how can we use that? Well, if we kind of look here at a problem, and I can say, okay, well, let's say that we had a problem. And let's say we want to know how much energy would be released when 50 grams of oxygen is reacted with excess CH4. Okay, and I just want to know, okay, well, I know that if I look up here and I look at the balanced chemical equation, the thing that this is telling me is that if I have oxygen and oxygen is my limiting reactant, I know that I'm going to get 802 kilojoules of energy released for every 2 moles of O2 that's reacted. That's where that 2 comes from. So that's kind of my ratio there. If I was only reacting 1 mole of CH4, I'd get that 802. If I was producing 2 moles of water, I'd get that 802. So the energy change is also following that stoichiometry. And so in this case here, if this reaction said, hey, how much energy is released when 2 moles of oxygen is released? It's easy. It's 802. Right? But I don't have 2 moles, I have 50 grams. And so what I have to do is I have to do a little bit of work, and I can say, okay, well, I know that I have 50.0 grams of O2. And again, you guys are really good at this. I know that for every 1 mole of O2, I have 32.0 grams of O2, and that's going to tell me that I'm going to get 1.56 moles of O2 that reacted during this reaction because it was a limiting reactant. Now, again, I want to know how much energy gets released, and so now if I know that I'm going to have 556 moles of O2, and then what I know is I get 802 kilojoules of energy released, and I'm going to put that in a negative sign there because that's released. All right, for every 2 moles of O2 reacted, that's going to give me a grand whopping total of negative 1250 kilojoules. Right, and so that would be my answer right there. Or I can kind of say 1250 kilojoules of energy is released. Okay, so the thing about the negative sign is it's just directional. It is doing this. So you don't see here it out front over here because I'm telling you it's released. And so that negative sign is just telling me, is it endothermic or is it exothermic, right? It's important because there's a big difference between an endothermic and exothermic reaction. Okay, guys, so that's kind of our energy changes and looking at endothermic and exothermic reactions and why they're going to be endothermic or exothermic. Let me know if you have any questions, and make sure you're doing a daily task for today. All right, guys, peace, love, happiness. Thanks for playing.